Pressure vessels are exceedingly important in the industry. Normally, two types of pressure vessel are used in common practice, such as cylindrical pressure vessel and spherical pressure vessel. In the analysis of thin-walled cylinders subjected to internal pressures, it is assumed that the radial plans remains radial and the wall thickness does not change due to internal pressure. Although the internal pressure acting on the wall causes a local compressive stress, its value is negligibly small as compared to other stresses, and hence, the state of stress of an element of a thin-walled pressure is considered a biaxial one. Further in the analysis of thin-walled cylinders, the weight of the fluid is negligible.
Welcome! Today, I will be discussing about thin-walled pressure vessels. To begin our investigation of pressure vessels, let's consider the internally pressurized cylinder shown below. First, we take a plane which is normal to the axis of the cylinder and use it to create an imaginary cut in the cylinder. After cutting the cylinder, we retain the back half of the cylinder. Remember, since this was an imaginary cut, the gas in the remaining half of the cylinder does not escape. This portion of the cylinder is still pressurized. The cylinder has a thickness T and a radius R. This analysis is limited to thin-walled pressure vessels. For a cylinder to qualify as thin-walled, the ratio of radius to thickness, or R over T, must be at least 10. The internal pressure, which is still acting on this portion of the cylinder, is represented in the pressure field shown below. The pressure is constant over the entire cut of the cylinder. Note that we draw the pressure in a manner which tends to inflate the cylinder. If the pressure acts in the opposite sense to that shown below, the following analysis must be used with caution. When we load vessels with external pressure, the loading can result in buckling or crumpling of the cylinder. In order for the free body diagram to satisfy equilibrium, there must be some force which counteracts the internal pressure. When analyzing thin-walled pressure vessels, it is assumed that all stresses act parallel to the surface of the vessel. This is often called membrane action. In the cylinder below, the only stress acting on the cut which can counteract the internal pressure is the normal stress, gamma 2. Gamma 2 is also called the longitudinal stress in the cylinder. At this point, we have enough information to apply force equilibrium in the longitudinal direction. The figure above represents the fact that the force caused by the internal pressure must be equilibrated by the force caused by the longitudinal normal stress. Remember, stress and pressure is expressed in units of force over area. To include stresses and pressures in force equilibrium equations, you must multiply the stress or pressure times the area on which it acts. The areas acted on by the longitudinal stress and the pressure are calculated in the figure above. Once we have figured the areas, we can calculate the forces caused by the pressure and the normal stress as shown above. We have made a major assumption here. Do you know what it is? Equilibrium requires that the forces be equal if the cylinder is to remain stationary. And the result is longitudinal stress is equal to PR over 2T. We call this stress in a cylinder the longitudinal stress because it acts parallel to the long axis of the cylinder. We just calculated the longitudinal stress. Is this the only stress acting in a pressure-filled cylinder? Let's cut the cylinder in a different manner and see. This time, our cut is parallel to the axis of the cylinder. After the cut, we retain the bottom half of the cylinder. Again, The gas has not left the portion of the cylinder shown below. It is still pressurized. But our cutting does not stop there. Next, we remove a slice of the cylinder which is of length delta L. What remains after our slicing and dicing is a half pipe of length delta L. Our previous analysis addressed the pressure which acts on this element in the longitudinal direction. What other pressure would act on this? This time, we will look at the pressure acting on the element in the vertical direction. Again, as we have drawn it, the pressure tends to inflate the element. The only stress acting in the vertical direction, which can counteract the pressure shown on the previous page, is the normal stress, gamma 1. This stress is called the hoop stress, because it acts like a steel hoop around a wooden barrel. It is time again to enforce equilibrium. Here we are focusing on forces which act in the vertical direction. The necessary area calculations are shown below. And here are the equivalent forces. Equating the two forces, we arrive at the expression for the hoop stress shown at the right. Hoop stress is equal to PR over T. This is the summary of the stresses in a cylindrical pressure vessel. For the longitudinal stress, it is equal to PR over 2T. For the hoop stress, it is equal to PR over T. We will now solve problems regarding stresses on thin-walled vessels. Problem number 1. A cylindrical pressure vessel is fabricated from steel plating. It has a thickness of 20 millimeters. The diameter of the pressure vessel is 450 millimeters, and its length is 2 meters. Determine the maximum internal pressure that can be applied if the longitudinal stress is limited to 140 megapascals and the circumferential stress is limited to 60 megapascals. Here is the illustration of the vessel involved. We can see that the radius of the vessel is 450 millimeters across. There is a thickness of 20 millimeters on both sides of the vessel. And also, the length of 2 meters is shown. The forces acting upon the vessel is the force downward and the resisting force upward. If we take the summation of forces vertical, we will get F is equal to 2T. From our formula, F is equal to stress times the area. In this case, area is equal to diameter times the length. T is represented as gamma tangential and length tangential. From the formula of circumferential stress, it is equal to PD over 2T. Substituting the given, we'll have 60 is equal to P times 450 millimeters over 2 times 20 millimeters. The pressure calculated is 5.33 megapascals. We now solve based on the longitudinal stress. If we take the summation of forces horizontal, we'll get F is equal to P. From the equation, F is equal to pressure times the area. In this case, the area is 1 over 4 pi d squared. The area is 1 over 4 pi d squared. P is equal to gamma tangential times pi d. From the formula of tangential stress, PD over 40, we substitute all the given. We'll get the P equivalent to the value of 24.89 megapascals. Since 5.33 megapascals is lower than 24.89 megapascal, we will get the governing P, which is 5.33 megapascals. Next problem. The wall thickness of a 4 feet diameter spherical tank is 5 over 6 inch. Calculate the allowable internal pressure if the stress is limited to 8,000 psi. For the total internal pressure, it is equal to pressure times the area. In the spherical tank, the area is 1 over 4 pi d squared. For the resisting wall, F is equal to P. F is stress times the area, while P is pressure times area. Stress times pi diameter times thickness is equal to P times 1 over 4 pi d squared. From the formula of cylindrical stress, P times D over 4T, we substitute all the given values. This will lead us to a pressure a total of 208.33 psi.
Now that we have discussed about thin-walled cylinders, let's now go to the types of failures. Such a component fails when subjected to an excessively high internal pressure. While it might fail by bursting along a path following the circumference of the cylinder, under normal circumstances, it fails by bursting along a path parallel to the axis. This suggests that the hoop stress is significantly higher than the axial stress.